Welcome to today's Explainer. We are navigating what I like to call the Mad Max Fury Road of Cambridge exams. Seriously, it is an absolute wasteland of tricky, deceptive questions out there. But today we are going to navigate that wasteland and claim your grade A-star treasure. Whether you're sitting syllabus codes 0625, 0652, 0654, 0972, 5054, or the absolute beast itself, Physics 9702 for AS and A-level, mastering momentum and Newton's laws is entirely non-negotiable. I mean, it appears in every single examination series. Every single one. We're looking specifically at the heavy hitters: force equaling mass times acceleration, linear momentum, where P equals mv, and force as the rate of change of momentum. Now, I want you to picture a real Cambridge physics past paper question, right in front of you. On one side, we have a student named Alex. Now, Alex completely overloads his paper with raw physics facts. He's literally dumping every single equation he's ever memorized onto the page, but there is absolutely zero critical analysis, just a wall of text. On the other side, we have Sam. Sam is panicking, rushing against the clock, furiously calculating numbers, and completely missing the command word requirements hidden in the prompt. If you could see their papers, they are just covered in red pen marks. They are leaking marks left and right. In this explainer, we are going to completely transform those red marks into green check marks by decoding the exact strategies you need. Okay, let's dive right into our roadmap for today. We'll start with the core principles, move smoothly into technical methodology, tackle an interactive workshop on mastering critical analysis, and finish up with the top 3 examiner warnings. Let's get to it. We have to begin by addressing the single biggest problem students face when they are sitting there sweating under the harsh exam hall lights. I want you to really absorb this quote, straight from an examiner alert. Even if your final answer is wrong, method marks can save you. This is what we call the method mark strategy. Look, physics is not just about getting the final number right. It's really not. It is about the process. It's about structured, logical reasoning. Think about it. If you miscalculate the final velocity of a colliding trolley just because you accidentally dropped a decimal point in your calculator, you might lose one single accuracy mark. Big deal, right? But if you fail to clearly show you're working, if you fail to explicitly state the principle of conservation of momentum, or if you fail to show that the initial momentum equals the final momentum, well, then you lose every single method mark attached to that entire question. Your process is your ultimate safety net in this wasteland. Remember our student Sam from a minute ago? Sam rushed the calculation, completely botched the final answer, and because there was zero step-by-step working shown, Sam scored a 0. 0 marks out of 5 possible marks. That is an absolute disaster, and the crazy part is it could have been completely avoided by simply writing down the foundational equation and substituting the values logically before touching a calculator.
Moving right along to Section 1, Core Principles. Let's break down the theoretical foundations every top-performing student absolutely must exhibit.
Here's the truth. You cannot simply memorize the textbook and expect an A-star. You have to actively decode the specific command words in the prompt. This is exactly where top students bring in the PEEL framework: point, evidence, explanation, link. You make your physics point, you provide evidence from the given data, you explain the physical phenomenon, and then you link it right back to the context. But before you can tackle complex, unfamiliar contexts with this framework, you need an ironclad, bulletproof grasp on these 2 specific definitions governing motion. First up, linear momentum. P equals mass times velocity. Seems incredibly simple, right? But here's the catch. Velocity is a vector. That means momentum is inherently a vector quantity. If a toy car moving to the right bounces off a wall and moves to the left, it has negative momentum. Forgetting that negative sign is literally the #1 reason candidates mess up collision calculations. Now look at the second definition: force as the rate of change of momentum. Newton's second law isn't just F equals ma. Its true, most powerful form is that the resultant force equals the change in momentum divided by the change in time. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's play a quick mental game to test this. Imagine 2 answers explaining why a crumple zone in a car is effective. Answer A says, crumple zones reduce force because F equals ma. Answer B says, crumple zones increase the time taken for the car to stop. Since force equals the change in momentum divided by time, a larger time results in a significantly smaller impact force. Which one actually follows the PEEL framework? It's answer B for sure. It explains the exact mathematical relationship and links it perfectly to the real-world context.
And this comparison perfectly illustrates the massive differences in academic benchmarks. Listen closely. Examiners are actively, aggressively prioritizing your analytical depth over a superficial spread of knowledge. Let's break down what analytical depth actually looks like. It means you are taking one very specific principle, let's say the conservation of momentum, and you are applying rigorous, logical, structured reasoning to a closed system where no external forces act. You are painting a picture for the examiner of the exact mechanics of the collision. Now contrast that with superficial breadth. This is exactly what our student Alex was doing, remember him? Alex wrote a massive paragraph about Isaac Newton's personal history, randomly mentioned kinetic energy, and threw in the word friction, just hoping something, anything, would stick to the mark scheme. Let me be clear, vague, disconnected facts will earn you nothing. Examiners have a highly specific mark scheme, and they are hunting for very specific keywords. When you're dealing with force and momentum, they desperately want to see phrases like resultant force, constant mass, isolated system, and vector quantity. If you aren't using the vocabulary, you aren't playing the game.
Let's transition into Section 2, Technical Methodology. It's time to build the procedural framework that translates that physics knowledge into actual exam marks.
This right here is where we initiate the transformation. We are taking those bleeding red pen marks and turning them into brilliant green check marks, using the physics success blueprint. The crucial takeaway is that you must follow this exact procedural checklist. Let's run a mental simulation. Imagine a question asking you to calculate the force exerted by a jet of water hitting a solid wall. Step 1. Extract the data. We have to identify the mass of water hitting the wall specifically per second. That is our rate of change of mass. Step 2. Apply the correct format. I'm putting a 60-second timer on the clock in your mind right now for a rewrite attempt. How do we format this cleanly? We carefully lay out the algebra. Force equals delta mv over delta t. Since the water stops completely dead upon impact, the final velocity is 0. We plug in the numbers, step by step, clearly showing the substitution. Step 3. Use appropriate terminology. Do not, under any circumstances, call it speed if you actually mean velocity. Do not just vaguely say the momentum changes. You need to say the rate of change of momentum determines the resultant force. Using the correct scientific lexicon is what proves to the examiner that you are functioning at a rigorous A-level standard.
And let me emphasize something absolutely critical. Presentation is not optional. Strictly adhering to formatting conventions directly develops the professional, scientific skills the syllabus actually demands. We're talking about crystal clear annotation on your graphs, proper, standard headings on any data tables you are asked to construct, and absolutely vital, the absolute non-negotiables, significant figures and units. Think about it. If you crunch the numbers and calculate a force of 25.432 newtons, but the raw data in the prompt was only given to 2 significant figures, you must round your final answer to 25 newtons. If you don't, you lose the accuracy mark. And never ever forget to write the capital N for newtons or key GM per S for momentum. Following these strict conventions is literally the easiest way to protect the method marks you've worked so hard to earn. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Let's level up to Section 3, Mastering Critical Analysis. This is where we elevate to higher-order assessment objectives and enter our interactive workshop. All right, we are going to see exactly how to build a perfect comparative analysis. This requires you to identify both sides of the coin and back everything up with concrete evidence. We're kicking off our interactive workshop with 2 challenges. Challenge 1 is a data scan. I want you to imagine a complex physics data table on screen right now, and you've got 60 seconds to extract the core trend. What's the relationship between the variables? You have to spot it fast. Now for Challenge 2, find the flaw. I'm going to read a flawed sample physics paragraph from a real past paper, and I want you to mentally highlight the sentence losing marks. Ready? Here it is. Elastic and inelastic collisions are both events where objects crash. In an elastic collision, kinetic energy is saved, but in an inelastic one, it is lost to the surroundings. Therefore, the forces are different. Okay, did you spot the flaws? Let's break it down with some examiner commentary. The flaw is twofold here. First, the student used incredibly vague, non-scientific language. Words like saved and lost to the surroundings are simply not acceptable at this level. You must say kinetic energy is conserved. Second, they completely failed to use comparative connectives and concrete evidence based on the requirements we see in this table. A flawed A-star comparative analysis would sound like this. While both elastic and inelastic collisions conserve total momentum, they differ because kinetic energy is strictly conserved only in elastic collisions, whereas it is converted to thermal energy in inelastic collisions. Boom! That is how you secure the marks.
Now for Challenge 3, speed writing. When drawing evidence-based conclusions, you must critically evaluate the quality of your evidence by actively looking for specific structural weaknesses. I'm going to give you a scenario, and you'd normally have a 30-second timer to write one perfect Peel paragraph. Here is the prompt. A student calculates the final velocity of a dropped ball just before it hits the ground using purely potential energy to kinetic energy conversions. Evaluate this approach. Okay, look at the bullet points we have here. You need to immediately identify assumptions. What is the student blatantly assuming? Air resistance. A perfect, top-tier answer during a speed writing drill would state, the conclusion is limited because it assumes a perfectly closed system with absolutely no air resistance. By completely ignoring the work done against air resistance, the calculated final kinetic energy, and thus the final velocity and momentum, will be artificially high. The alternative interpretation is that drag forces actually reduce the net resultant force acting on the ball, thereby significantly reducing its rate of change of momentum. That, my friends, is how you demonstrate masterful critical analysis.
Finally, we arrive at Section 4, Top 3 Examiner Warnings. Let's see where the final pitfalls are hidden.
We are diving directly into the principal examiner reports here to uncover the exact reasons candidates leak marks on exam day. And to combat this, we're introducing the final system, the 3 rules that guarantee top marks: command word decoding, Peel framework application, and a time management matrix. Now, what's really fascinating about these top 3 examiner warnings is that they have absolutely nothing to do with not knowing the underlying math. It's entirely about failing to apply the knowledge to the precise scenario. Warning number 1, answers are far too vague. If a question asks why a gas exerts pressure on the walls of a container, you cannot just casually say the particles hit the wall. You have to specifically state that the gas particles collide elastically with the wall, experiencing a distinct change in momentum. Since force is the rate of change of momentum, the wall exerts a force on the particle, and by Newton's third law, the particle exerts an equal and opposite force on the wall. Warning number 2, forgetting format conventions. This means leaving out units, messing up your significant figures, or drawing sloppy, unlabeled force vectors. Don't do it. Warning number 3, providing answers not specific to the context given. If the question is clearly about a spacecraft in a vacuum, please do not write an entire paragraph about air resistance just because you memorized a mark scheme from a parachute question last week. Context is absolutely king. Decode the command word, apply Peel, and manage your time to check your context.
So, how do we actively avoid these traps when the clock is ticking down? You should create a personal memory hack, an acronym for the variables affecting momentum to lock in that crucial specific context. I like to use the acronym VMTD. V stands for vectors. You must always check your direction signs. Is it positive or negative? M stands for mass. Is the mass constant, or is it an open system like a rocket burning fuel, creating a constantly changing mass? T stands for time. Are we looking at the specific collision time, which dramatically affects the final impact force? And finally, D stands for dynamics. What are the external forces acting on the system? Is there friction? Is there drag? Remembering VMTD will act as a trigger for your brain to systematically check every single required variable under those high-pressure exam hall scenarios. It's a lifesaver.
As we wrap up this explainer, I want you to look back at your past paper practices and honestly ask yourself this one vital question to guarantee you capture every possible method mark. Are your conclusions strictly evidence-based? Every single time you make a statement about Newton's laws or a change in linear momentum, you need to point directly back to the data table, the graph, or the foundational equation. Don't be an Alex who overloads the page without structure, and definitely don't be a Sam who rushes and entirely misses the command words. Be the strategist. Decode the exam, flawlessly apply the Peel framework, and extract every single mark available to you. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.